All right, one more FRQ to take a look at here. This is one pretty similar to one we did in the notes. The continuous function f is defined on the interval from -4 to 3 inclusive, and there's -4, there's 3. And useful bit of information, this is the graph of f. So it can't be anything else, it is the graph of f. Okay, and that's good to know. Now, the graph of f will consist of a couple of quarter circles and one line segment, as shown in the figure above. And then let g of x be defined as 2x plus the definite integral from 0 to x of f of t dt. Now again, this 0, that's not throwaway information. Okay, in fact, nothing is ever throwaway information in an FRQ. So now that we know all this, let's tackle some questions related to this particular situation. Okay, we're going to start by finding g of -3 and then find g prime and evaluate g prime of -3. All right, well, let's start with g of -3 first. And let's do that one. And let me get the right tool here. If I'm going to find g of 3, then I'm going to plug in this, or -3 rather, then I'm going to need to plug in this -3 everywhere I see an x inside my function g. So 2 times -3 plus the definite integral from 0 to -3 of f of t dt. That's how g is defined. And now what I need to do is start evaluating. And I get to this part, and that's great, but this other part I start to go, all right, I may have a problem here, because it looks like my upper limit of integration is actually less than my lower one. So maybe we put the flip-flop on this and change the limits of integration rather selfishly using one of my infamous properties of mathematics here, integrals. And now if I'm looking at this part right here, the definite integral from -3 to 0, remember that's the area under the curve. And if this is indeed the graph of f, then this right here is the area that I am going to use my time wisely on. And I've already been told that that's a quarter circle, so in order to find the definite integral here, I am not going to think too hard on this at all. I'm going to use my understanding that this is a quarter circle, and when I go to find that particular area of that quarter circle, I'm going to notice that it has a radius of 3, so 3 squared is 9, and since it's a fourth of a circle, we're looking at 9 over 4, or maybe 9 pi over 4 actually. And that is all the further that I am intrigued by this problem. I'm going to put a stop to this foolishness right here and now. I think that's a pretty good guesstimate for the area under the curve and the value of g of -3. Okay, well now to find g prime of 3. Let's go ahead and find g prime of x first, because that might be helpful to our cause. If I go to find g prime of x, I'm going to end up with 2 plus, oh, okay, well hang on here. This is just going to be f of x according to fundamental theorem part 1. All right, that's good to know. So now, to find what g prime of -3 is, it's going to be 2 plus f of -3. All right, well, I know what 2 is, but how do I get f of -3? I'm going to get it from the picture here, and f of -3 is going to occur right at this specific point, right there. So f of -3 is 0, and therefore we should end up with 2 as our answer there for that particular part. Very, very fascinating question to help us come up with the parts there. And pretty cool question, actually. All right, let's move ahead. We are to determine the x-coordinate at which G has an absolute maximum. Okay? Well, let's think about this. I mean, we've got to think about the idea for part B that the absolute maximum occurs at a critical point. Well, where could that be? That could be at endpoints, or it could be at point in the middle where the derivative is 0. So where could those things possibly be? Well, maybe a sign chart will help us. And if I start at negative, whoopsies, let's get the right tool here. If I start at x is equal to -4, and I really do not want this. I want the pen, for crying out loud. I don't know why I keep getting that. Okay, so start at -4, work my way to 3, and I've got a derivative of 0 at -3, and what appears to be 1 1/2. Okay. This has to do with G, though, so we've got to be careful here and make sure that we get this right, where G has an absolute maximum. So let's go back and recall what the derivative of G of x is. The derivative is going to be -2 plus f of x. So I guess if this is going to be 0, then this occurs when f of x is equal to 2, -2 rather. All right, now where does that occur? Well, here's -2. It's going to occur right there, so it's probably safe to say that that's going to happen at x is equal to 5/2. Okay, now the reason why we weren't looking so quickly at other places, and I stopped myself, was we had to deal with G here, which had that extra factor of 2x in it when we defined it. So that is going to be our absolute maximum there at x is equal to 5/2. Okay. All right, now the next part says find all values of x on this interval where we have a point of inflection. And we want to know where there is a change of slope. You're looking for a change of slope. So as you kind of follow along from left to right here, the slope appears to be positive until we hit an x value of 0, and then we have a sudden change from positive to negative, and the slope of this remains negative all the way to the end. So there is only one spot for which there is a point of inflection, and that's at x is equal to 0, and the reason is a point of inflection, to be specific here, because f prime of x, which is equal to g double prime of x, changes slope at x is equal to 0. That part wasn't so bad. Pretty easy to come up with. Okay, now this one, you thought the previous part wasn't so bad. This part isn't as bad as it might look either. Find the average rate of change of f on this interval from -4 to 3. And then it goes on to say there is no point for which f prime is equal to that average rate of change, and we're to explain why. This does not contradict the mean value theorem. Okay, well, let's get back to that in just a moment. Let's find the average rate of change, and the way to do that, when we see the words average rate of change, this is just code for slope. So if I found the average rate of change, then I basically need to find the slope of f of 3 minus f of -4 all over 3 minus -4. Okay, now where do I get f of 3 and f of 4? Well, from the graph, of course. Here is f of 3. It's negative 3. Woohoo, that was easy. Where is f of negative 4? Right there. It is negative 1. So a little bit of math later, and I'm going to come up with negative 2 over 7 for the slope. Okay, now let's kind of review what the mean value theorem says to help us answer this second part. This does not contradict the mean value theorem. Why? Well, for the mean value theorem to work in the first place, the function must be continuous on a closed interval, and it must be differentiable on every point inside that interval. So as I look at this particular function, surely it's continuous. I'm told so in the prompt. But this function is not differentiable at x is equal to 0. There is a sharp change of slope at that point. So this statement, this does not contradict the mean value theorem because f is not differentiable on negative 4 to 3, not inclusive. Okay, so that's the reason why that's the case. Nice little review of Unit 5 there. All right, folks, that's that question.